And now in this lecture we'll find out the area of the circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have the circle. We know that side AB of the quadrilateral is equal to 2 units, side BC equals to 8 units, and side DC also equals to 8 units. This angle DCB equals to 90 degrees, and this angle ABCD is also equals to 90 degrees. Our mission is to find out the area of this circle. So first of all we'll do a construction. We'll extend sides DA and CB until they touch each other. And we will define the touching point of the two sides AD and CB as M. So here CB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. We extended the straight line CB by a straight line, and the result is CM. When you extend a straight line by a straight line, the result must be a straight line, therefore CM is a straight line. So here CM is a straight line. If you focus on the upper side of the straight line CM at point B, the sum of the angles on the upper side of CM at point B must be equal to 180 degrees. According to the rule, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. Okay. So, we'll focus on the right triangle at BM, and we'll define this angle as theta. In the right triangle in BM, this angle equals to theta according to our definition, plus this angle is equal to 90 degrees, plus the missing angle. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. So, why it is 90 degrees minus theta? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. So we focus on triangle DMC. On the big triangle DMC, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. So, in the next step, we will prove that the big triangle MDC is similar to the small triangle MAB. Okay, so I write it down. The big triangle MDC is similar to the small triangle MAB. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is angle DCB that belongs to the big triangle, angle DCM that belongs to the big triangle, and it is equal to this angle, angle ABM, that belongs to the small triangle ABM. So I repeat again. Angle DCM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta that belongs to both triangles. It is a common angle, therefore angle theta equals to itself. If we relate to angle theta as it belongs to the big triangle, it will be defined as angle DMC. And it is equal to itself. If we relate to angle theta as it belongs to the small triangle, it will be defined as angle AMB. So this equation means that angle theta equals to itself. We just call to angle theta two different names. Again, angle theta is a common angle that belongs to both triangles, therefore angle theta equals to itself. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So write it down. This is angle CDM in the big triangle. And it is equal to this angle, angle MAB in the small triangle. Repeat again. Angle CDM equals to angle MAB. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the three angles in the small triangle, in the big triangle MDC, are correspondingly equal to all the three angles in the small triangle MAB. Therefore proved that the big triangle MDC is similar this is the sign of similar to the small triangle MAB according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all the three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule, exactly as we proved in these two triangles. From the fact that the two right triangles are similar to each other, we will conclude that the following relationship exists between their sides. We conclude that MC in the big triangle over MB in the small triangle is equal to DC in the big triangle over AB in the small triangle. Repeat again. MC over MB equals to DC over AB. What is the length of MC? From the drawing, it is very easy to see that MC equals to MB plus BC. That is to say, MC equals to MB plus BC, and BC is 8, so in total MC equals to MB plus 8. So we substitute MC by MB plus 8 over MB is equal to DC over AB. DC is 8 and AB is 2, so in total DC over AB is 8 over 2. 8 over 2 is 4, so 4 equals to MB plus 8 over MB. We multiply this equation by MB and we get that MB plus 8 equals to 4 times MB. We subtract MB from this equation. And we get that 8 equals to 4 MB minus MB, it is 3 MB. We divide this equation by 3. And finally we get that MB equals to 8 over 3 units. So I found out that line segment MB, this line segment MB equals to 8 over 3 units in its length. In the next step, we will implement the Pythagoras theorem on the small right triangle ABM. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABM is AM, therefore the square of the hypotenuse is AM squared. And it is equal to AB squared plus MB squared. So according to the Pythagoras theorem, the right triangle ABM AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, so AB squared is 2 squared, that is 4, plus MB squared. We just right now found out that MB equals to 8 over 3, therefore MB squared equals to 8 over 3 squared. So AM squared equals to 4 plus 8 over 3 squared. 8 over 3 squared equals to 8 squared, that is 64, over 3 squared, that is 9. So AM squared equals to, here we multiply 4 by 9 and then we divide it by 9 in order to have a common factor with 64 over 9. So 4 times 9 is 36, so we have in the numerator 36 plus 64 over 9. 36 plus 64, it is 100 over 9. We take a root out of this equation and finally we get that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3, and finally we found out that the hypotenuse AM equals to 10 over 3 units in its length. So in the next step, I present to you rule number 1, and we implement rule number 1 in our drawing, but before that, here AB is tangent to the circle at this point. We define the point of tendency as M, and here also BC is tangent to the circle at this point. We'll define the point of tendency as N. And we'll define the center of the circle as O. Now we present to you rule number 1, and we'll implement rule number 1 in our drawing. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB, that is tangent to the circle at point M. And we have the radius OM. So the radius OM, it is drawn to point M, that is the point of tendency of tangent AB with the circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. So we can implement rule number 1 in our drawing. Why? Because in our drawing we have here, we join points O and M together by a straight line. Point O is the center of the circle. Point M is the point of the circle itself. This is exactly the definition of a radius. So OM is the radius of the circle. We'll define the radius of the circle as x. So here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, we get that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and N together by a straight line. ON is the radius of the circle that we defined as x. The radius ON, it is drawn to to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent BC with this circle, and therefore, according to rule number 1, tangent BC will be perpendicular to the radius NO. If BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We'll focus on quadrilateral MOBN. Inside this quadrilateral MOBN, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Therefore, the fourth angle must be equal to 90 degrees, because 270 degrees plus 90 degrees, it is 360 degrees. That is the sum of the angles in any quadrilateral. Okay. In the next step, we will draw perpendicular on BC in such a way that it will be also tangent to the circle. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular with BC as G so the perpendicular is tangent to the circle. At this point we define the point of tendency as F. We join points O and F together by a straight line. OF is the radius of the circle that we defined as X. Again, we have the radius OF that is drawn to the point of tendency, that is to say it is drawn to point F, that is the point of tendency of tangent GF with the circle, and therefore GF will be perpendicular to FO. If GF is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle it is also equals to 90 degrees, according to rule number 1. So we'll focus on quadrilateral ONGF. In quadrilateral ONGF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Angle FOM, this angle, is equal to 90 degrees plus 90 degrees, it is 180 degrees. Any angle that is equal to 180 degrees, it is a straight line. Therefore, FOM is a straight line. Actually, here, FO is the radius x. MO is also the radius x. So, the only question that can be asked there is whether if at the point of the at the touching point of the two radii, if they create with each other a straight line, because for 100% MO as the radius must be a straight line. FO as the radius must be also a straight line. But the only question that can be asked there, whether if in their touching point, that is to say, at point O, the touching point of the two radii, if they create between them a straight line. And because of the fact that at their touching point, this angle equals to 180 degrees, it means that at their touching point, the two radii create between them a straight line, therefore FOM is one straight line. FOM is one straight line, and again, we have this FO is the radius, MO is the radius, and therefore FO plus OM is 2R. It must be the diameter of the circle, and we can also explain why Fm is the diameter of the circle, because of the fact that Fm is the straight line, because in this angle FOM equals to 180 degrees, therefore Fm is the straight line. But Fm also touches the circle at points F and M, and therefore Fm is a chord. Fm is a chord that passes through the center of the circle. And we have the rule that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, Fm is the diameter of the circle. So you can write here that line segment Fm is the diameter of the circle. Fm is the diameter of the circle. Fm is the diameter of the circle. In the next step, we focus on quadrilateral FMBG. In quadrilateral FMBG, this quadrilateral, we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral FMBG as a rectangle. Okay, quadrilateral FMBG is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, Fm equals to Bg. You can write down that in rectangle FMBG, Fm equals to Bg. Fm equals to Bg. But we just right now found out that Fm is the diameter of the circle. And from this equation, Bg equals to Fm equals to the diameter, we will derive that Bg also is the diameter of the circle. Bg is the diameter of the circle. This line segment Bg is the diameter of the circle. And we also know that the diameter of any circle is twice as long as the radius, and the radius of this circle is x, therefore the diameter must be 2x. So Bg equals to 2x in its length. You can write down here that Bg, line segment Bg equals to 2x in its length. Okay. So, in the next step, we will extend the perpendicular GF until it touches side DM. And we will define the touching point of the extended GF and MD as K. So here we have the right triangle MKG. This is the right triangle MKG. In the right triangle MKG, this angle equals to 90 degrees. This angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. So in the next step, we'll prove that the big right triangle MKG is similar to the small right triangle ABM. Okay? Again, the big triangle MKG is similar to the small right triangle ABM. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle KGM in the big triangle equals to angle ABM in the small triangle. Repeat again. Angle KGM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles, so angle theta equals to itself. If you relate to angle theta as it belongs to the big triangle, it will be defined as angle KMG. And it is equal to itself. It is equal to angle theta to itself. So if we relate to angle theta as it belongs to the small triangle, it will be defined as angle AMB. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. Again, angle theta it is a common angle that belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle GKM in the big triangle. And it is equal to the small angle BAM. Repeat again. Angle GKM in the big triangle equals to angle BAM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangle MKG are correspondingly equal to all the three angles in the small triangle ABM. Therefore, the big triangle MKG is similar, this is the sign of similar, to the small triangle ABM according to angle similarity rule. And from the fact that the two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that MG in the big triangle over MB in the small triangle equals to KG in the big triangle over AB in the small triangle. Repeat again. MG over MB equals to KG over AB. MG, from the drawings it's very easy to see that MG equals to MB plus BG, that is to say MG equals to MB, that is 8 over 3 plus BG, that is 2x, so in total MG equals to 8 over 3 plus 2x. Okay, so we substitute MG by 8 over 3 plus 2x over MB, that is 8 over 3, plus kg. Kg is unknown, so we leave it as it is. Kg over AB. AB is 2, so we substitute AB by 2. So here we'll multiply 2x by 3 and then we divide it by 3 in order to have a common factor with 8 over 3. And we'll get that 8 plus 2x times 3 is 6x over 3 over 8 over 3 is equal to kg over 2. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And we'll actually get that after we cancel 3, we have here 8 plus 6x over 8 is equal to kg over 2. Okay. So here we first multiply this equation and we get that two times 8 plus 6x equals to 8 times kg. Here we divide this equation by 2 and finally we get that 8 plus 6x equals to 8 over 2 is 4. So here we get 4 kg. So here we divide this equation by 4 and finally we get that kg equals to 8 over 4 is 2 and 6x over 4 is 1.5x. So in total we found out that kg equals to 2 plus 1.5x. So I can write down in the original drawing that kg equals to 2 plus 1.5x. 9 segment kg or side kg. This is 9 segment kg. That is equal to 2 plus 1.5x. Okay. So because of the fact that the big triangle KGM is similar to the small triangle ABM, addition relationship exists between their sides. The following relationship exists between their sides. MG in the big triangle over MB in the small triangle equals to KM in the big triangle over AM in the small triangle. And again, MG over MB equals to KM over AM. I already explained to you that MG equals to 8 over 3 plus 2x, so substitute mg by 8 over 3 plus 2x. Over mb, that is 8 over 3. And it is equal to km. Km, for the drawing, it is ready to see that km equals to ka plus am. That is to say km equals to ka plus AM. AM is 10 over 3. So in total, KM equals to KA plus 10 over 3. AM equals to KA plus 10 over 3. Over AM. AM is 10 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to have a common factor of 8 over 3, and here also we'll multiply Ka by 3 and then we divide it by 3 in order to have a common factor of 10 over 3. And we will get that eight plus 2x times 3 is 6x over 3 over 8 over 3 equals to 10 plus 3 times Ka is 3 Ka over 3 over 10 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And here also we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So after we cancel 3, we left only with, here in this of the equation, we will have 8 plus 6x over 8. It is equal to 10 plus 3 Ka over 10. Repeat again, after we cancelled 3, we left only with 8 plus 6x over 8 equals to, again, 8 plus 6x over 8 equals to 10 plus 3k over 10. We will cross multiply this equation and we get that 10 times 8 plus 6x equals to 8 times 10 plus 3 Ka. So here we'll open the brackets on both sides of the equation and we get that 8 times 10 is 80 plus 8 times 6x is 60x and is equal to 8 times 10 is 80 plus 3 times 8 times 3 Ka is 24 Ka. So here we have 80 on both sides of the equation, so 80 will get cancelled, and we left only with 60x, that is equal to 24 Ka. Here we'll divide this equation by 24, and finally we get that Ka equals to 60x over 24 is equal to 2.5x. So in conclusion, we found out that 9 segment Ka equals to 2.5x. So we can write here that this 9 segment AK or Ka, this 9 segment AK is equal to 2.5x in its length. Okay. In the next step, I will copy quadrilateral A, B, G, K in a new page. So actually, this is quadrilateral AKBG that I covered from the original drawing. This quadrilateral AKBG blocks a circle. This is the circle that the quadrilateral blocks, so I copy the circle here, the new drawing. the circle and the quadrilateral as 4 points of tangencies. They are tangent to each other at 1, 2, 3, 4 points. We define the first point of tangency as M. We define the second point of tangency of the quadrilateral with the circle as N. We'll define the third point of tangency of the quadrilateral and the circle as L. And finally, we define the fourth point of tangency of the circle and the quadrilateral as T. Okay. In the next step, I present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, whenever you draw two tangents to a circle from a common external point, then the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common external point, point A, from the common external point, point A, we have two tangents to this circle. We have tangent AM and tangent AT. And according to rule number 2, AM equals to AT. Tangent AM equals to tangent AT. So if AM equals to A, then AT must be also equal to A. The next step will focus on the common external point, point B. From the common external point, point B, we have two tangents to the circle. We have tangent BT and tangent BL. And according to rule number 2, BT equals to BL. Tangent BT equals to tangent BL. So if BT is B, then BL must be also equal to B. We focus on the common external point, point G. From the common external point, point G, we have two tangents to the circle. We have tangent GN and tangent GL, and according to rule number 2, they must be equal to each other. So GN equals to GL, GN equals to GL. So if GN is C, then GL is also C. And finally, we focus on the common external point, point K. From the common external point, point K, we have two tangents to this circle. We have tangent Km and tangent Kn. According to rule number 2, they are equal to each other. So if Km is D, then Kn must be also equal to D. Okay, so in the next step, we will add side AK to side BG in quadrilateral AK BG. AK plus BG. AK plus BG. Okay. we add side AK to side BG in quadrilateral AKBG. From the drawing it is very easy to see that AK equals to A plus D. Okay, so we substitute AK by A plus D plus BG. From the drawing it is very easy to see that BG equals to B plus C. In conclusion, we found out that AK plus BG equals to A plus D plus B plus C. If we change the order of the variables, this expression it is actually equals to A plus B plus C plus D. Okay, A plus B plus C plus D. In the next step, we'll add side AB to side KG in quadrilateral AKBG. So AB plus KG. From the drawings, it's very easy to see that AB equals to A plus B plus KG. KG equals to C plus D. In conclusion, found out that AB plus KG equals to A plus B plus C plus D. So both AK plus BG and AB plus KG, they are both equal to A plus B plus C plus D. Therefore, of course, they are equal to each other. So you can write down that AK plus BG is equal to AB plus KG. Okay. AK equals to 2.5x, so therefore we substitute AK by 2.5x plus BG. Here BG equals to 2x, therefore we substitute BG by 2x, and it is equal to AB. AB is 2, therefore we substitute AB by 2, and finally plus KG. Here KG equals to 2 plus 1.5x. So we substitute kg by 2 plus 1.5x. In conclusion, we found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x, and is equal to 2 plus 2 is 4 plus 1.5x. Here we subtract 1.5x from this equation, and finally we get that 4.5x 4.5x plus 1.5x is 3x. That is equal to 4. Here we'll divide this equation by 3, and finally we get that x equals to 4 over 3 units. X is the radius of this circle, that is equal to 4 over 3 units. Okay, and we know that the area of any circle, here the squared brackets is the sign for the area, so the area of any circle is equal to pi times the radius square. So if the radius is r, it is pi r squared. Now a specific circle, we define the radius as x, so the area of our circle will be equal to pi times the radius square, pi times x squared. We just right now found out that x equals to 4 over 3, so we substitute x by 4 over 3, and we will get that radius of our circle will be equal to pi, and x is 4 over 3 square. Pi times 4 over 3 square. 4 over 3 square equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. And that is the answer to our question. In the next step, I will summarize the lecture. In this lecture, we found out the area of this circle. In the drawing, we have quadrilateral ABCD. Inside this quadrilateral, we have this circle. We know that side AB of the quadrilateral equals to 2 units in this length, side BC equals to 8 units, side CD equals to 8 units also. This angle ABC equals to 90 degrees, this angle DCB equals to 90 degrees, and our mission is to find out the area of this circle. So first of all, we did a construction. That is to say, we extended side DA and side CD, side DA and side CB in such a way, we extended them until they touch each other. Okay, so this point is their touching point, so we define the touching point as M. And then we extended side CB, that is a straight line by straight line, and we got line segment CM. When you extend the straight line by straight line, the result must be a straight line. Therefore, CM must be also a straight line. CM is a straight line. So if you focus on the upper side of the straight line CM at point B here, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. Okay, 90 degrees plus 90 degrees, it is 180 degrees. So this angle equals to 90 degrees. We focused on triangle A and B, the right triangle A and B. We define this angle as theta. So this angle equals to theta according to our definition. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees. Why? Because 90 degrees, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. Then we focus on the big right triangle MDC. In the big right triangle MDC, this angle equals to theta, this angle equals to 90 degrees, and for the same reason, this angle must be equal to 90 degrees minus theta. In the next step, we proved that the big triangle MDC is similar to the small triangle MAB. Why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, therefore we can say that angle theta equals to itself, and finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually prove that all the three angles of the big triangle DCM are correspondingly equal to all the three angles of the small triangle ABM. Therefore, the two Right triangles are similar to each other according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all the angles in one triangle are correspondingly equal to all the angles of another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule, exactly as we proved on our two triangles. From the fact that the two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that MC in the big triangle over MB in the small triangle equals to DC in the big triangle over AB in the small triangle. I repeat again. MC over MB equals to DC over AB. MC, from the drawing, it is very easy to see that MC equals to MB plus BC, that is to say MC equals to MB plus BC, that is 8. In total, MC equals to MB plus 8. So substitute MC by MB plus 8 over MB equals to DC. DC is 8 and AB is 2, therefore DC over AB is 8 over 2. 8 over 2 is 4, so MB plus 8 over MB equals to 4. We multiply this equation by MB and found out that MB plus 8 equals to 4MB. We subtracted MB from this equation and finally found out that 8 equals to 4MB minus MB, this is 3MB. 8 equals to 3MB. We divided this equation by 3 and finally found out that MB equals to 8 over 3 units. This line segment of this side MB equals to 8 over 3 units. In the next step, we implemented the Pythagoras theorem on the right small triangle MAB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle AB, it means that AM square equals to AB square plus BM square. Repeat again, in the right triangle AMB, according to the Pythagoras theorem, AM square equals to AB square plus MB square. So AM square equals to AB square. AB is 2, so AB square is 2 squared, that is 4, plus MB square. We just right now found out that MB equals to 8 over 3, therefore MB square is 8 over 3 square. So AM square equals to 4 plus 8 over 3 square. AM square equals to 4, and 8 over 3 square equals to 8 square, that is 64, plus 3 square, that is 9. So AM square equals to 4 plus 64 over 9. Then we multiplied 4 by 9 and then we divided by 9 in order to have a common factor with 64 over 9. So AM square equals to 4 times 9 it is 36 plus 64 over 9. 36 plus 64 is 100 over 9. We took out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3. So in total we found out that AM equals to 10 over 3 units. The hypotenuse AM here equals to 10 over 3 units. Okay, so in the next step I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. Tangent AB is tangent to this circle at point M. We have the radius OM that is drawn to the point of tangency, that is to say it is drawn to point M. That is the point of tangency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tangency, then the tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule number 1. We can implement rule number 1 in our drawing. Why? Because here the center of the circle is at point O. Then AB is tangent to the circle at point M, and BG is tangent to the circle at point N. We have point O is the center of the circle, point M is the point of the circle itself. This is exactly the definition of a radius. Therefore, OM is the radius of this circle that is defined as X. We have the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And therefore, tangent AB will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We join points O and N together by set line. ON is the radius of the circle that is equal to X. We have the radius ON that is drawn to the point of tendency. Therefore, tangent BG will be perpendicular to the radius NO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. In quadrilateral OMBG, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus 90 degrees. In total, it is 360 degrees. That is the sum of the angles in any triangle. So this angle must be equal to 90 degrees. Okay, then we do perpendicular on BC, here BC, in such a way that the perpendicular will be also tangent to this angle at point F. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. Point F is the point of tendency, for tangent KG with the circle, according to our construction also. We join points O and F together by set line. OF is the radius of the circle that is drawn to the point of tendency. It is drawn to point F, that is the point of tendency. Therefore, tangent KG must be perpendicular to the radius FO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So in quadrilateral OF and G, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Okay, so actually we found out that angle FOM, this is angle FOM, it is equal to 90 degrees plus 90 degrees, it is 180 degrees. So any angle that is equal to 180 degrees, it is a straight line. So FOM that is equal to 180 degrees, it is a straight line. FOM is a straight line, therefore FM is also a straight line. But it is a straight line that touches the circle at point F and at point M. Therefore, FM is a chord. FM is a chord that passes through the center of the circle. That is to say, it passes through point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, FM is the diameter of the circle. Yeah. FM is the diameter of the circle. Then we focus on quadrilateral MFBG. In quadrilateral MFBG, we have 1, 2, 3, 4 right angles. Therefore, quadrilateral FMPG is a rectangle. Why? Because any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral MBGF as a rectangle. In a rectangle FMBG, the opposite sides must be equal to each other. That is to say, FM must be equal to BG. FM equals to BG. But we just right now found out that FM is the diameter of the circle. And from this equation, BG equals to FM equals to the diameter, we will derive that BG is also the diameter. This line segment BG is the diameter of the circle. The diameter is twice as long as the radius. The radius is x, therefore the diameter is 2x. That is to say, the diameter BG equals to 2x. BG equals to 2x in its length. Okay. In the next step, we extended the perpendicular of GF until it touches side DM at point K. This way, created the right triangle KGM. In the right triangle KGM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Then we prove that the right triangle KGM is similar to the small right triangle ABM. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, therefore angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangle KGM are correspondingly equal to all the three angles in the triangle ABM. Therefore the two right triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, Others will conclude that the following relationship exists between their sides. We will conclude that MG in the big triangle over MB in the small triangle. MG in the big triangle or MB in the small triangle equals to KG in the big triangle over AB in the small triangle. KG over AB. So MG over MB equals to KG over AB. Here mg equals to 8 over 3 plus 2x. Again, mg equals to 8 over 3 plus 2x. So we substitute mg by 8 over 3 plus 2x over mb. mb is 8 over 3. kg is unknown, so we leave it as it is. ab is 2, substitute ab by 2. So 8 over 3 plus 2x over 8 over 3 equals to kg over 2. We multiplied 2x by 3 and then we divided by 3 in order to have a common factor with 8 over 3. And there we got that 8 plus 2x times 3 is 6x over 3 divided by 8 over 3 equals to kg over 2. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. What is left from this equation after we cancelled 3? We have 8 plus 6x over 8. This side of the equation. We have 8 plus 6x over 8 equals to kg over 2. Because multiplied this equation, we found out that 2 times 8 plus 6x equals to 8 kg. We divided this equation by 2 and found out that 8 plus 6x equals to 8 kg over 2 is 4 kg. We divided this equation by 2 and finally found out that kg equals to 8 over 4 is 2 and 6x over 4 is 1.5x. So in total kg equals to 2 plus 1.5x. Here. kg equals to 2 plus 1.5x. Okay. Because of the fact that the right big triangle KGM is similar to the small right triangle ABM, we conclude that addition relationship exists between their sides. We conclude that MG in the big triangle over MB in the small triangle equals to KM in the big triangle over AM in the small triangle. Repeat again, MG over MB equals to KM over AM. MG is 8 over 3 plus 2x. Again, mg is 8 over 3 plus 2x. mb is 8 over 3. What is the length of km? From the knowing, it is very easy to see that km equals to ka plus am. That is to say, km equals to ka plus am, that is 10 over 3. So in total, km equals to ka plus 10 over 3. Km equals to Ka plus 10 over 3 and Am is 10 over 3. Here we multiplied 2x by 3 and then we divided by 3 and here we multiplied Ka by 3 and then we divided by 3. And we found out that 8 over 3 plus 2x times 3 is 6x over 3 over 8 over 3 equals to 10 plus 3 times Ka is 3Ka over 3 over 10 over 3. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also we have 3 in the numerator and 3 in the denominator, so 3 here also will cancel. So what is left from this equation after we cancelled 3 on both sides of the equation? Here we have 8 plus 6x over 8 equals to 10 plus 3ka over 10. Repeat again. 8 plus 6x over 8 equals to 10 plus 3ka over 10. We first multiply this equation and finally found out that 10 times 8 plus 6x equals to 8 times 10 plus 3ka. We opened the brackets on both sides of the equation and found out that 8 times 10 is 80 plus 8 times 6x is 60x equals to 8 times 10 is 80 plus 8 times 3ka is 24ka. Here we have 80 on both sides of the equation, so we cancel the 80. And we're left only with 60x, that is equal to 24ka. Here we divided this equation by 24 and finally found out that ka, line segment ka, equals to 60x over 24 is 2.5x. So here, line segment ka equals to 2.5x in its length. This is line segment ka, that is equal to 2.5x in its length. Then I copied quadrilateral A, B, K, G here in a new page. This is quadrilateral A, K, B, G that I copied. Inside this quadrilateral, we have this circle that is blocked by the quadrilateral, so I copied this circle. The circle and the quadrilateral have 4 touching points. They are tangent to each other at 4 points. M, N, L, and T. Then I presented to you rule number 2 and implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to the circle. We have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, whenever you draw two tangents from a common external point to the circle, the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. We can implement rule number 2 in our drawing. If you focus on point A, from point A we have two tangents to the circle, tangent AT and tangent AM. And according to rule number 2, AT equals to AM. So if AT is A, then AM must be also equal to A. Then we focus on the common external point B. From the common external point B, we have two tangents to the circle, tangent BL and tangent BT. And according to rule number 2, BL equals to BT. So if BL is B, then BT must be also equal to B. And then we focus on the common external point G. From the common external point G, we have tangent GL and tangent GN. And according to rule number 2, they are equal to each other. That is to say, GL equals to GN. So if GL is C, then GN. If GL is C, then GN must be also equal to C. And finally, we focused on the common external point K. From the common external point K, we have two tangents to this circle, tangent KM and tangent KN. And according to rule number 2, they are equal to each other. That is to say, KM equals to KN. So if KM is D, then KN must be also equal to D. Then we added side AK to side BG in quadrilateral AKBG. AK plus BG. What is the value of AK plus BG? AK, from the drawing it is very easy to see that AK equals to A plus D. So we substitute AK by A plus D, plus BG. From the drawing it is very easy to see that BG equals to B plus C, so we substitute BG by B plus C. In conclusion, found out that AK plus BG equals to A plus D plus B plus C. We can change the order of the variables and we will get that AK plus BG equals to A plus B plus C plus D. Then we added side AB and side KG. We added side AB to side KG in quadrilateral AKBG. AB is A plus B. KG is C plus D. So in total, AB plus KG will be equal to A plus B plus C plus D. So both AK plus BG and AB plus KG, they are both equal to A plus B plus C plus D, therefore they are equal to each other, of course. So we can write down that AK plus BG equals to AB plus KG. Okay, so here AK equals to 2.5x, therefore we substitute AK by 2.5x plus BG. BG, this is BG, this is equal to 2 plus 1.5x, so substitute KG by 2 plus 1.5x. And it is equal to AB, AB is 2, so substitute AB by 2, and finally plus KG. K plus KG, here KG, actually KG, it is equal to 2.5x. So actually, you have here AK, again AK is 2.5x, plus BG. BG is 2x, so we substitute BG by 2x. And then it is equal to AB, that is 2, plus KG, that is 2 plus 1.5x. So in total, AK plus BG equals to AB plus KG. It means that 2.5x plus 2x equals to 2 plus 1.5x. 2.5x plus 2x is 4.5x. And it is equal to 2 plus 2 is 4 plus 1.5x. Here we subtracted 1.5x from this equation and found out that 4.5x minus 1.5x is 3x. So 3x equals to 4. We divided this equation by 3 and finally found out that x equals to 4 over 3. That is to say the radius of this circle x is equal to 4 over 3 units. And we know that the area of any circle, the square brackets is the same for the area. It means the area of any circle is equal to pi times the radius square. If r is the radius, it is pi r square. In our specific circle, the radius is x, so it is the area will be equal to pi x square. We just right now found out that x equals to 4 over 3, so we substitute x by 4 over 3. So pi x square is pi times 4 over 3 square. Pi times 4 over 3 square, it is pi times 4 over 3 square. 4 over 3 square is 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 units. Okay? The area of the circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.